Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or you are amongst the 50% of the people watching this who have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a super chat that runs alongside the show while it is live, so toss me a buck or two if you are enjoying these live debates. And most importantly, if you would like to join the discussion, there is a link in the info box below this video. Yes, there is. With the page you are currently watching on mute, simply click that link to join the discussion and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number one, please do not swear. If you do, you will be ejected. And if you are, please do not try to rejoin the stream using sock accounts. You will be warmly welcome back on the next stream. Now, in a moment, I'm going to transition straight across to the Hangout, as we have got one guest already in who's hoping to screen share, who I'll introduce in a moment. But I will encourage everybody who is currently in the live stream to please share the show. This is something that I will periodically ask the chat to do, as it's the most important thing as far as I'm concerned an audience member can do, as it increases the live audience, which in turn increases the likelihood of having a more diverse panel. So please share the show. And one last time, if you are new to this channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. So our first guest in the Hangout is Sleeping Warrior. How are you doing?
Morning, Nathan. I'm good.
To have you here.
Couldn't stay up last night to watch your evening show. I fell asleep because it was a long weekend, so I've missed two. So catching up now.
Fair enough. Did you say you wanted to share something? Because I actually got you all queued up, hence us being a little bit late to start. If you wanted to share that.
Screens, yeah.
Tell me when you're ready and I'll pull you up.
Right, I'm on now. So if you can present it, and hopefully whilst this is working, people in chat can tell me whether or not they hear the system sounds when I play a particular file. Let me just test that first, because I'm going to play the file. Just tell me if people can hear it. Reality of the position is if it's actually true that the ISS is the height that it's at. So yes. Could the chat hear something about ISS then?
Yes.
Great. All right. Where to start with this little nugget of info? I think I'll start with, thanks, just to let you know we're live.
Okay, would you like a mince pie?
Yes, please, thank you. Right, so I've missed the last show. I was ready to go yesterday morning, didn't get it because Nathan was out with Santa duties. And I missed the evening show, so I've kind of missed two, even though there was only one. And I'm going to start with the angular size discussion, because the angular size discussion rumbles on. I think the best way to describe this is the way Curved said. He admits that he doesn't necessarily really know all about this, which is fine. That's honest. That's fair. That's fair dinkum. But in yesterday's show, they were Curved was talking about the triangle calculator, and that was the best part of the show for me because it was the most on topic. So I want to do a bit of a recap, but I also want to do it in direct application to the International Space Station, because this is the bit that we can make it all make sense. It's abundantly clear that flat earthers don't get the angular size point. They think that it's simply the measurement of the angle, and that's the angular size, and that's not correct. The observer on Earth, looking at the International Space Station, for example, can measure the angle, but unless you know the actual size of it or the distance, you don't get to know the rest of you don't get to know how big it is. Now, obviously this started with when I asked Lewis, how did he know the distance to the sun? And Nathan said, good question. And then Lewis kind of went away with the fairies and he never really answered it. And he said that it was because he thought it was a stupid question and he ignored it. Although it looks as though he just didn't know how to answer it. But you can interpret it any way you wish. But from then, this has rumbled on because it directly links you into the angular size discussion. And the angular size, when you look at any definition or most definitions, they all say the same thing. The angular diameter or the angular size is an angular measurement describing how large a sphere or circle appears from a given point of view. It's a specific point of view. It's not any point of view. It's a specific point of view. And that's the bit that the ballers are refusing to address. For 2 weeks, I was laughed at because everybody said how stupid I was. The angular size is just the measurement of the angle. And everybody, all the ballers were saying, no, you've lost this point. Come on, just admit it. You were wrong. And I was like, no, you guys don't understand it. So it rumbled on. This is one of the things I cited in the discussion. Just press mute, if you would. The angular size of an object is determined by its actual size and its distance from the observer. You do need both, okay? And I was abundantly clear, and it was never accepted. So yesterday's debate, Curved brought up this part, which was the calculation of the other parts of the triangle. And he was correct to point out that you need 3 parts of it. If you know the observer's angle and you know another observer's angle, provided you know the distance between the two, you can calculate the rest of the triangle. That is true. You need 3 pieces of information. The 3 pieces that you can't, the only 3 pieces that won't give you anything is the 3 internal angles. Because if you get 3 internal angles, you're just going to get a sum that equals 180. You need you need at least one distance and 2 angles if you're to get the rest of the details. But with regards to the sun, we don't know the distance to the sun, so we're trying to work that out. We don't know its actual size, the angular size, so we're trying to work that out too. But this only works if we live on a flat plane. That's the bit that Curved didn't really get, because this isn't flat on a ball. This is curved. So,
well, they do. Sorry, just to interject, just because there's no ballers here to say it. They do have the maths to do that, though. They do insert that presupposition into the trigonometry.
I haven't seen anything for that, so maybe if the likes of Paul or maybe Curved are out there, they can show that.
It's the reason you get the distances that you do. I mean, if you calculate it using spherical trigonometry, you end up with huge distances to the stars. That's why you end up with huge distances to the stars, because of that presupposition.
Indeed, but I don't think Curved had got to that point last night. He only got to this point, which is the application on a flat plane. So, I mean, credit to Curved for going out and looking for something. But what he cited was actually what the flat earthers would cite, because this is what we would use to triangulate stuff, to try and calculate the values. And there was a particular video, which I won't go into, but it was one that Jaron did. It's an old one. And the point was that if you apply spherical maths to it, you get huge distances. And if you apply flat maths to it, you don't. So I'm not going to cite that because it's not part of this, but you're right. There is stuff out there, but Curved didn't present this the other night. So based on what Curved presented, I'm just responding and reacting based on what he's presented.
Without being too rude, how much longer do you have on your presentation? Just because we've got a couple of guests that I want to say hello to you. They're turned down at the moment, but Miles and Arav, you will get an introduction in just a moment, as soon as Anthony's finished this presentation, which hopefully won't be too long.
Thanks. So what when we're trying to establish the distance to the sun or the moon, we can't work them out, because to get the distance to the sun, you have to know the distance to either the moon or to Venus. And to get the distance to the moon or Venus, you need to know the distance to Venus or the moon. It's a circular reference that doesn't give us the answers that we need. So what I realized was that there is something up there that most flat earthers generally accept to be factually there, although that's debatable. But for the purposes of this, we're just going to assume that the International Space Station is a tin can, and it is orbiting the Earth at 410 kilometers away. We also know the size of it. So if you know the actual size and you know the total distance from the observer, you can work out what the angular size is. Now, somebody's already done the maths here, and he basically says, assuming the overhead ISS is at 400 kilometers and a maximum dimension of 100 meters, which isn't too far out, you can work it out to get the angular size, which is the point I was making a few weeks back. You need to know the distance, but you get the angular size, and you can do it in degrees, arc minutes, or indeed arc seconds. But then you can apply that on Baller's evidence. So here we've got a still taken from Red's Rhetoric's video recently, where he's got the P900 capturing the International Space Station transiting the moon. So if we know the actual size of the make that a bit bigger. If we know the actual size of the International Space Station and we know its distance to the observer, that then gives us something that we can upscale from a ratio point of view to see how does it compare to the moon. Because if the ISS is where they tell us it is, the moon should be in the right place behind it, and the maths should verify up. They should do the same thing. So what I did is, maths isn't my strongest point. So what I did is I spoke to Hector, with Chris Monk, and I asked them both, could one of them do the maths? I wanted to know, could they do the maths to test the actual size, the angular size of the moon based on the known parameters of the International Space Station? Now, this is a minute long, but basically, I'm not going to play the whole lot, but the bit I want to play is the bit where he calculates it. And he actually did all this directly in relation to the angular size of the moon based on the angular size of the International Space Station at 410 kilometers. So listen to what he says. Say that again.
With the moon being at the point where it is furthest away, so the 405 kilometers of distance,
yeah,
I'm getting a result of 16.5 times the ISS size.
16.5 times bigger.
Yeah, but the moon is 16.5 times as big as the ISS in your image.
All right, so that would be 16.5 times the size of the ISS. So if you just stack 16 ISSs, right, then that's the calculated diameter of the moon, right?
Yeah.
All right, so basically the maths to get the ratio is that we should get 16.5 International Space Stations. If you stack them all in a line, you should get 16.5 to get the angular size of the moon. And then the distance should be the same. It should be 240,000 or maybe 260,000. So when we've then put this information into the computer and modeled it, the results that we got were not quite what we expected. The moon turns out not to be 260,000 miles away. Now, what I'm going to do for the moment, I'm going to give way and let Miles speak and let other people come on. And further into the show, I'll come back and show what actually we did get. And then maybe people can then respond. So all I'm doing at the moment is laying the seeds. According to the maths, to get the ratio of the angular size of the International Space Station, when you cross-reference that against the moon, they should give you the distance to the moon similar to 260,000 miles. Should, right? But it didn't happen. So I'm going to pass the mic away to somebody else now. Let them speak, and hopefully we can talk about angular size in relation to the ratio of the moon. But maybe it won't go there. But we'll try. So Nathan, if you want to introduce Miles.
Off mute. Right, so we've been joined first and foremost by, I think Miles was the first one in, so good to have you, Miles.
Good morning.
Very pleased to see you. And then next we had Arave. How are you doing?
Doing good, Harry.
I'm very well indeed. Good to have you here. And last but not least, we have Make 4. How you doing?
Hey.
Hey.
So I was listening to Anthony's the last part of Anthony's presentation there, and he seems to have things somewhat wrong already in the maths. Am I being heard?
Yeah.
Everything seems to have frozen.
Even just looking at that picture, it doesn't really look like you could. I'm not sure if I understood it properly, but it looked like there was more than 16 or 17 of those things next to each other. Is that what we were counting?
Well, that doesn't really matter. The point is the angle is for the size, so it's angular size. Now, if you're placing that in front of an object that is much further away, then the two arms that form that angle, if you like, continue to diverge, and so
Correct.
The actual distance across the moon, represented by the ISS, there is considerably greater than the width of the ISS.
Yes, but I haven't done the maths. Somebody else.
Unless you know the distance to the moon, which we do, because it's been measured by radar, by laser reflection, and by a number of other methods. You can't calculate what that actual distance is. Only the angle or angular size. Agree. Angle and angular size are the same thing.
One second.
No,
how do we?
I don't agree, Miles.
That would be
well, then you're wrong.
How do we know the distance to the moon?
How do you know the distance to the moon?
Yeah.
It's been measured by laser reflection is the most accurate method.
Is that the only way though that we've got is just by pinging it?
No, there are other methods that have been used as well, but that's the most accurate.
Well, let me just address the laser point.
That's allowed scientists to measure the distance to the moon to just a few centimeters error, which over 240,000 miles approximately, or whatever it is in kilometers, is pretty remarkable.
Can I just clarify
Yeah,
this? So, sorry, Anthony. So what you're referring to, Miles, is an observatory in the States that is specifically set up to fire a laser at the moon reflectors that were left by the Apollo astronauts to give us a return signal. And I've watched this, admittedly not in person, but on a video. I think it was Brian Cox that went there. Didn't really understand why he was going there and what the point was, but nonetheless, this was the point, to prove the distance to the moon. And what the single operator did, was sit in front of a computer, press a button, and then something appeared on her screen. That's what actually happened at the observatory.
Well, that's what you saw on that program. That's not. That doesn't.
My point is, Miles, that this observatory is run specifically.
When you go in for a brain operation, you don't assume that the surgeon is just going to take a saw, cut your head open, chop a bit out, and stick it back together again. You actually trust that the expert in the field has done the work properly.
Sure. In that example, though, Miles,
all the research
Miles, in that example, Miles, there will be left a scar on my head, and you could film that happening, and there could be plenty of ways to refer to how it's happened. In the case of the observatory, which is government run, government funded, that observatory, A, isn't accessible by me. I can't do that experiment. And B, there is no physical evidence to show that that has actually happened, unlike a scar on my head if I have brain surgery.
And I think the point he's trying to say, Miles, is that it's falsifiable. Not necessarily that it was, but that it is. So therefore it lacks credibility.
It's perfectly possible to falsify almost anything, even a brain operation. The point is that you disregard stuff that distance is measured, is known. All the information
measured by government agencies
to check that it's been done properly is out there. Now, if you still want to claim it's fake, then why bother with any of this at all?
We can't do it, though. We're looking for things we can do, Miles.
And say
rather than
everything
trusting
is fake.
people.
I'm the only one that knows anything.
I mean, if we took that to the extreme, Miles, we'd just Google it, wouldn't we? We'd just Google it and just accept the answer we got.
Right?
So anyway, like let's say.
Can you say that again, Nathan?
He said we'd Google it. If we wanted to know stuff, we'd just Google it and we'd accept any answer that we would.
Not at all. And that is not remotely what I said.
Well, that is what you said.
Let's make the connection here. I mean, the thing is, the general principle still works. Like an object that's viewable at one distance will, at twice the distance, have size. And so, using those laws, you know that with, like Daniel Robotham said, you can see objects basically up to 3,600 times their size in the distance, and you can use math. So like a 1-inch penny will be viewable from 3,600 times its size of 1 inch off in the distance based off of your height. Okay, and it's the same thing with the space station. If we know the space station's height of 400 kilometers, it should be visible before it disappears at the vanishing point at 3,000 times 400 kilometers of its size. And knowing that about the moon, if you zoom in on the moon, depending on how much angular size it increases or decreases, you know its size based off of the way that it looks with the zoom. And that's based off of the law of triangles. An angle of 15 degrees opens up to half of the amount of a 30-degree angle. Based off of triangles, which relates to perspective too. So it's all, triangles.
Absolutely. And this calculation of the space station angular size and comparing it to the size of the moon probably would allow you to calculate the size of the moon. What I'm saying is that the calculation, or the way that Anthony's presented it so far, that calculation appears to be wrong. They're doing it in the wrong way.
I would sort of agree.
It seems to be the same principle.
Can I respond? Because I haven't had a chance to respond to the calculation allegation, because I didn't actually do the calculation. The calculation was done by a ball earther by the name of Hector, a mutual friend called Hector, and he's the physicist that Paul claims to be. Now, when he's done the maths on the ratios and the trigonometry and the tan thetas and all that kind of stuff, he was the one that calculated it. Now, if you assert that he's got the maths wrong, I could play the video showing all of the maths if you'd like and tell me where he has gone wrong. But I did have a second guy that was doing it who was also a baller by the name of, not Hector, Hillel Finder. and they were both cross-referencing each other, and they're both ballers. So if you want to assert that either of them have got the maths wrong, be my guest. We can go through it now if you'd like.
The way you presented it was wrong. I'm not saying they've got the maths wrong. I'm saying the way that you presented the ISS being 16 widths of the moon or whatever, 16 widths of the ISS equals the width of the moon, does not appear to be correct.
I agree. It does not appear to be correct. That was the test we were trying to test. We were trying to see.
No, the calculation is not correct.
Do you agree, if we know the angular size of the International Space Station, we can ratio that up to work out what is the moon's distance and is it consistent with what they tell us? Do you agree that that can be done?
You can, if you know the angular size, you know the actual size of the space station, you know the angular size of the space station, you know the distance to the space station. Correct. If you can have an image of that across the moon, what you can do is calculate the angle, and you can say that the portion of the 2 points from either end of the space station will give you a size on the moon.
Okay, so that's not really
from that, you ought to be able, if you can then multiply that up, you ought to be able to then calculate the distance to the moon.
Right, but that's not actually how the maths works. The way the maths works
is how the maths works.
Well, not according to Hector and according to Thingy, it's not. Hillel Finder. They both did the maths. So the way it works is this. That you calculate the angular size of the International Space Station, and then based on Red's rhetoric's evidence...
You do know that's going to have quite a big error because of the difficulty in actually... you've got a very small object on the screen there, and you're measuring... It's very difficult to get an accurate angle for that from the observer.
That was all considered in the maths. We didn't do the maths. The ballers did the maths, and they came back with at the end. I mean, I can show you the whole maths if you like, and you can tell me where it goes wrong. But I think
what was the conclusion?
16.5 is the expected size of the moon. It's 16.5 times bigger than the International Space Station. So if I was to play
16.5 times the extrapolated length. So it's not 16.5 times the ISS. It's 16.5 times the length that you extrapolate from that angle.
No.
Well, now we can figure out how far the moon is based off of those calculations. The vanishing point is at 1 second. So it'll be twice as big when it's twice as close at 2 seconds of arc, all the way up to a degree, which would be 60 times the vanishing point distance, all the way up to when it's right up in your face, like a degree away, 3,600 times from the vanishing point. So if we know the size of the sun, we get the vanishing point and multiply that times 3,600 or whatever, and that's the distance.
Well, I don't mind playing the clip again for you, Miles, just so you can hear it again. But this is what he actually said. Listen carefully, and you can hear what he actually said.
What distance did they come up with? What size for the moon did they come up with? What distance did they come up with?
Well, we did the distance. They worked out what the ratio was.
Oh, you did the distance, so they didn't work that out for you.
No, they worked out the ratio, and then we applied the ratio.
Okay, so all you've got from them. So your claim that the ballers who are physicists did this maths for you. All you got from them was
they're actually not ballers.
The 16.5.
Right.
Is that right?
When you say all you got from Miles, let's put what your Miles, wait.
To the
Miles.
Small size, it's not been extrapolated up to the size across the moon.
Miles, let me put what you've just asked into context. He did the maths he did the trigonometry. That bit, we're all right with the trigonometry bit. It was the ratio bit that we needed to know. We needed to know how many ISSs would fit into the moon if the moon is 260,000 miles away. So I'm going to play the clip again and listen to what he said, okay? Hector, in the side chat, I've put the video for what Reds did, and you can see by looking at like the first 25 seconds, you can see that the angle
is virtually. I'm only hearing it.
Oh, hang on, that's not the right video. That's the long version. Let me put the shortened version up. Hang on. And then the clip that I wanted wasn't that. Just bear with me a sec while I get it.
It's just audio, Miles. Don't worry.
It was just so that you can hear his answer. This was like after an hour's worth of discussion, calculations and stuff. This wasn't 2 seconds. I couldn't do it myself. We couldn't do it. It was literally, we needed a baller to do it. So we asked would he do it, and he did.
Take
Really
that
what we're
long to
testing
work
here, I
out.
suppose, is just listen to what he says. Did somebody pluck the figure out of the ISS height out of thin air, or did they actually calculate it before they told us? That would be the skeptical position. The reality of the position is, if it's actually true that the ISS is the height that it's at, it should correspond with the same angular size for the moon.
In the estimate with the moon being at its furthest point away from the Earth, I'm getting 16.5 times the size on the image.
Say that again.
With the moon being at the point where it is furthest away, so the 405 kilometers of distance,
Yeah.
I'm getting a result of 16.5 times the ISS size.
16.5 times bigger.
Yeah, but the moon is should be 16.5 times as big as the ISS in your image.
All right, so that would be 16.5 times the size of the ISS. So if you just stack 16 ISSs, that's the calculated diameter of the moon, right?
Yeah.
Right, so he's calculated 16.5 times the size of the ISS, according to the distance of 260,000 miles, which is obviously the distance to the moon. So he's calculated that, and obviously you can hear by my expression that I was shocked, because that's clearly
What was
less
the
than
angular
16.
size of the ISS as calculated?
Say again, Miles?
Yeah, how much of an angle does it occupy in your vision? What, half a degree, 1 degree, 2 degrees? How much?
What's the angular size of the ISS on that image?
The information that I suggested this as a template because somebody had already asked it, and in the long maths that he calculated, it was consistent with this answer. This guy's based it on 400 kilometers rather than the 410 that we were using.
Anthony, you're misunderstanding.
On
what
100,
was the
100
angular
meters in
size calculated
so the angular size,
from that
Miles,
image?
Miles, listen. So the angular size was either 0.01432 degrees or 0.86 arc minutes or 51 arc seconds. And when he did it based on the values that we were given.
Okay, let's take that. Yeah. That's
so
fine.
when he did it based on the other maths, it was comparable. So it means that we were checking this guy's maths, and it turns out that he was right. This guy's maths is right. But we did it on the values 410 kilometers and 110 meters, right? So we had a baseline to work with, and then from there you can then scale up the ratio to work out how many international space stations should fit inside the moon if the moon is the distance they tell us it is away. So we fixed the moon at that distance, and all we had to do was work out how many international space stations went inside the moon. That's
Come on, man! Even on like a flat Earth model, like. That space station, how big is that space station? Sorry, do you know the size?
Yeah, 110 meters in width.
So you're telling me that thing's like 1.6 kilometers, or 1.65 kilometers in the moon. You're saying the moon is a 1 kilometer wide?
Well, no. What I'm saying is we were testing the distance to the moon, and if we kept the distance to the moon fixed, and we knew the angular size of the International Space Station, you could ratio that up to work out how many International Space Stations should fit inside. When Reds has done this, make that bigger. Basically, we should be able to, because we know the angular size to the International Space Station, but we don't know the angular size of the moon. If we fix the distance to the moon, you can then ratio up how many International Space Stations should fit in the gap that is the moon, the diameter of the moon, and then that would give you. Well, assuming that the distance was correct, it should be the same. So it should be 16.5 international space stations.
The calculation is clearly incorrect, because if you take from point to point across that ISS, you would get a lot more than 16.5.
Exactly, that was the point of the experiment.
So that means that calculation of the angular size of the ISS is in error.
But that was done by two
billions of miles away. What if it's closer and the calculations are off anyway?
Oh, sorry, guys. I just want to introduce Paul. Sorry, Miles. Sorry, Paul. I just want to introduce Paul. How you doing, Paul?
Hi.
Good morning,
Nathan.
Paul.
Good to have you, Paul.
Good morning, Miles.
Let's see.
I see there's a
Paul.
bit of a drama going on here about angular size of the moon and angular size of the ISS. To be able to do the calculation and understand what's going on here, I need some figures from Anthony, because I don't honestly know these figures myself. What length are we using? What size are we using for the ISS here?
110 meters.
110 meters across for the ISS. Okay. And what distance are we using for the ISS?
We used 410, which is the value that you find most easily on Google.
So that'd be 410,000 meters. Okay. And what distance to the moon were you using?
260,000.
Can we put that in kilometers, please? Because it works out better for... Because if you're measuring the ISS in meters and the height of the ISS in kilometers, use all the same units, please. So let me just calculate that. What were you using? You were using how many kilometers? How many miles?
418,429 kilometers.
I didn't quite get that. You faded out there. What was that again?
418,429 kilometers.
That would be the absolute furthest distance. I think the average distance to the moon is only about 385,000 kilometers.
Yeah, I think they used the furthest distance possible for the ISS and the furthest distance possible for the moon for these calculations.
Okay, so can we put that at, say, 410,000 kilometers? Does that sound reasonable?
Put it any way you want.
Okay, and the diameter of the moon, I believe, is about...
No. Forget the diameter. Just work on the fixed the distance, because we were testing the distance to the moon.
No, I want
the moon.
to compare the sizes here. That's
the
whole point in doing. You'll see what I'm going to do in a moment. Okay. I might need some help because I don't have access to a good calculator with me here. The diameter to the moon is 3,474. I want to show you how this sort of jibes with everything, okay, and how they got those calculations. If I can, I'm going to try and
Paul. So long as you're answering the question, does the distance to the moon match the angular size of the International Space Station when you ratio it up? That's what we're working on.
I'm going to draw a diagram. Yeah, I'll see if I can share so you can see what I'm doing as I'm doing it here. Let me see what I can get up here. I want to do something. I'm not very good at doing paint sort of things, so bear with me.
What I'm going to say, guys, is while Paul does this, he's doing this on the fly. Bear with him. Please don't interrupt him. Let him get to the end.
So what we're going to draw here is two triangles. We're going to draw one triangle, and they might be a bit rough here, but hopefully I can give you an indication of what's going on. I've got to draw that one. Just ignore that line. This line's going to be wonky, but imagine that line straight and it joins up there. Okay, that's pretty bad, but one triangle is going to represent the ISS, and the other triangle is going to represent the moon. And you'll understand why I'm doing this in a moment. Okay, you're going to have to imagine that's a straight line. Sorry about that. If we take this one to be the ISS and this one to be the moon, all right, what we're going to do here is I'm going to show you how the angular size is what matters here. So what we're going to do, if this is the ISS, this line along here is the distance to the ISS, which I think you put at 410 kilometers. So that would be 410,000 meters, okay? Agree? All right. And this distance here is half the width of the ISS. So if you're putting it at 110 meters, then this would be 55. Oh, sorry, my mouse just did a funny thing. That would be 55 meters because we're looking at half the angular size. Do you understand that, Anthony? You get that? The full angular size would be there. I'm just taking half it, so it's a right angle triangle in here. Okay. What I'm going to need somebody else to do. Miles, do you have access to a calculator at the moment?
I do.
Yeah. calculate what angle that is in there for me by using the tangent formula. You need to do inverse tan of 55 divided by 410,000 and tell me what the angle in there is.
55 divided by
410 and then inverse tan and find out what the angle in there is.
So which angle are we measuring?
Measuring the angle that I've indicated here.
That one.
Yeah, so what you do is measure
actually
inverse tan of 55 over 400.
Wait a minute, tangent is, it's opposite over hypotenuse, isn't it? No,
yeah, so what you want to do is you want to do 55 divided by 410,000
over adjacent.
And then inverse tan that.
Yeah.
The angle.
Yeah, I don't think I inverse tanned, I think I tanned it. Hang on.
Yeah, you need to
This is great. You're all being really patient.
Coming out the same every time.
What's that? It'll be 0 point something.
Yeah.
Right. It'll be an angular.
Use calculator very often, so.
Yeah. I would normally use the calculator on my phone, but I broke my phone the other day, and I'm using a phone that doesn't have a very good calculator on it. It doesn't do inverse tans, so I just can't do that at the moment. So I'm relying on somebody else to do that for me here. And the other, while you're doing that, I'll put in the other calculation. For the moon, the diameter of the moon is 3,474. We need to halve that to get half the diameter. We need 3,474 divided by 2. That would be 1,737 kilometres for half the diameter of the moon. 1,737, and the distance to the moon was you said 410,000 kilometres. So
we've got an answer from chat,
which is the same number that we've got there.
Okay.
Up 410.
Oh, hang on, I've got a phone call to take. Sorry, guys.
I think we've got an answer from chat, from Alex Quant. 0.00013414634.
0.0. Now, was that the inverse tan? Because that doesn't sound right.
The answer is ... arctan open brackets 55/41 and then 4 zeros close brackets equals 0.00013.
0.000.
Yeah, 1341.
1341. That'll do.
Yep.
And then you do the same with these numbers. This one we would expect to come out to be about 1/4 degree.
Oh, he's using the octan. Octan. Should be the inverse tan.
Thanks for helping there, Make 4. You were really useful then.
Yeah, just hold off the trolling. Just till we get to the end of this. We're nearly there.
As long as we're still working towards how many international space stations should fit inside the moon, that's the answer that I hope Paul's going to come back with.
I actually did want to do this and get a second opinion.
Now,
So,
I am relying on somebody else to do this calculation for me. I can't
Yeah, it's
verify that
miles.
at the moment. So the only way I can verify it is to do the tangent of that angle and see if it comes out to be that value. 110,000 equals. No, that's not right. What he's done is he's simply done that number divided by that number to give that number. That's not what I asked. That is not right. Whoever supplied me with that has simply just done that number divided by that number. I'm not sure. Oh, hang on. No, that would be about right. Sorry, that's right. Okay, so now I need this one here. What that one there is.
like learn how to use a calculator.
I think he's
I
given
need
us
the
that as well.
arctan of that divided by that.
I think he's given us that as well. Let's have a
Yep.
look. He doesn't confirm. I don't know if he's just done a different. It says arctan open brackets 1773 / 41.
1737. 1737.
Sorry, I'll say that again. 1773.
No, he's got those reversed around. It should be 1737.
Oh, okay.
Alex,
Sorry,
do you want to check
one
your
more
maths?
time.
Now, obviously, I went through this yesterday with 2 of them, and I understand. And for anybody that's watching, Paul's actually doing something good here, so we'll give him the space that he needs to breathe, and we won't do anything bad, because I really want to get to the point where he gives the figure of how many times bigger the moon is to the ISS, working on their maths, because it should be about the same.
You're a physicist and you don't have a calculator.
No, his phone.
Give him a break. His phone broke.
Yeah, be nice.
Yeah,
to me,
that's
Paul.
right.
This is not
Yeah.
easy.
Yeah.
This is not
I
easy.
do normally have a calculator, but I just don't at the moment. So, yeah.
On any other day, you'd have got away with that kind of trolling, mate. To be honest,
Yeah, I would expect this to come out at around about 1/4 of a degree, 0.25. Okay.
And I agree, Nathan. Any other day, he'd have got away with that comment. But while he's actually doing it, we'll have to give him a bit of space.
For sure. No, this is good. It's good to get a second point on it.
Yeah,
like
because
someone
if we
else-
can get a similar figure, then we know that the maths has been done consistently between both people, and that makes it credible, right?
For shiz.
I'd hope so.
Alex Quant from the chat, the guy who's doing the calculation, says Google Calculator's got all of the functions you need.
What's that?
Google Calculator.
Oh, maybe I can do that. I'll just type it in my other thing and see if that comes up with it. Okay. I've just got to figure out how to do the arctan on it.
There seems to be websites for this as well.
Yeah, but if he does it raw himself, his own maths then is what he would rely on, because I don't think he'd want to trust the websites if he's able to do the maths himself.
Yeah, I'm just trying to find out.
I'm back now. Did you get to those figures or not? Did somebody else calculate?
No, I'm still waiting for someone to calculate this bottom one here for me.
Well, I think that's I'm not sure I got this absolutely right. I think the angle in degrees for the
yes,
the
that's
ISS.
Yep.
Did Anthony give you one for that?
I got an answer, but I'm not sure if it's correct because I haven't
I
been
come
able
up
to
with
verify.
0.000139746. So 3 zeros after the decimal point.
Yep.
139 or 140 if you want to.
I'll put 139.
Yeah.
All right. Can you do the same
Rounding it up.
calculation now for the bottom one, Miles, please?
For the bottom one.
The one.
Yeah.
Yep. I need the arctan of 1,737 on 410,000.
So it's 1737 divided.
Sorry, I missed a
by-
zero on that. That should be 410,000.
Yeah.
Yeah.
The same distance.
Yeah.
Oh,
One's
right.
meters
Okay.
and one's in kilometers. Right. So this whole lot's in meters. This whole lot's in kilometers. That doesn't matter because the ratio
Okay.
that matters. Yeah.
Yeah, I think that first one, I might redo that calculation because I just realised what I've done, what I might have done wrong.
Okay.
This one I come out with 0.24 degrees, 0.242 or 243 degrees.
That's what I would expect. That matches up with the angular size of the moon that we
Just
see.
redo the top one again, just make
thank
sure
you.
I've done that right.
If you can do that, yes, please. Okay. That is what we would expect for the angular size of the moon. Remember, that's half the angular size. The full angular size goes out to here. Okay.
Yeah,
so you double
actually,
that to get. Oh,
I
yep.
actually think the top one is the arc tan of the inverse
Yep.
tan of that is a lot higher. That top one.
Yeah, that's what I thought.
Yeah, it's not right. It's 0.00768.
0.00768. Okay. All right. So that's the angular size of the ISS in degrees. Well, half the angular size. It doesn't matter. As long as we're doing half and half, they're still comparable. So now what you do is you do this number, the 0.243, divided by the 0.00768. I can do that here too. And I get for that 31. All right, 31.6. But
Yep.
you now need to remember that that is half the angular size. And so what we would expect is that this number to be half that, okay, which roundabout works out to be about 16. All right, 15, 16, which is
what
actually,
Anthony.
Excellent.
which is about right.
Excellent.
Yeah.
That's
Okay.
good. Good to see that
So
done live.
does
Thank
that-
you. Thank you. Thank you.
Why
Does
is
that
that?
satisfy?
Wait, what
Can you just
exactly?
explain why it's half that?
Are you telling me that we can fit 16 ISSs across the moon, like side by side? Is that what that means?
No, that's not what it means.
Okay, what
That is
exactly
exactly
did
what
we
it means.
calculate? Because
No,
Yeah,
hang on.
that is exactly what it means. That's
means-
why we've just calculated it,
means-
Miles.
It means that the angular size of the ISS is about 1/30th that of the 1/31st of that of the moon. That's what I'm calculating here. That's what we would expect to see.
Okay, so
so
let
you
me
can
ask you
fit
the
that-
point
That's
blank
the
question.
calculation that I would expect to see.
Paul, are you at the position where you can tell me the answer to this question? How many times bigger than the ISS is the moon?
It depends on now what measurements you're taking. Okay, what you would need to do, you would need to literally, if you were going to do that, if you knew the distance to the ISS and the size of the ISS, and let's say the ISS was this square in here, can you see that? All right.
Well, we do know
what
the
you would
distance
do,
to the ISS.
what you would have to do to be able to measure the size of the moon by doing that, you would have to see how many times that square fit across the moon. You would literally
Right.
have to do that measurement. Okay.
But we've done that. But what I'm asking is, can you tell me how many? So, do you agree that 16.5 is there or thereabouts the maths?
Well, I'm getting 31.6 here is what you would expect. That's what I'm
Okay.
getting here. So I'm not
Now-
quite sure how the other two got the 16.5.
Okay.
But
now,
what
at this point,
even
I would.
talking about?
At
Can you
this point,
explain
I
that
would
then?
I
say
don't
that we
know
got
whether Miles agrees with me here. Would you agree with the calculation that I've done there, Miles?
This is the moon measurement. There is the radius. Is that right?
That moon measurement there is half the radius. So because that's why we're making a right angle triangle here.
It's half the diameter.
Half
isn't
the
it?
diameter of the moon, yes.
Yeah. So it is the radius. Yeah.
Yeah, that's right. The radius of the moon, that's the distance to the moon. This is the half the size of the ISS, and that's the
Yeah.
All right,
distance
well,
to the ISS.
So if you did the same calculation, with using the full diameter of the moon, the full width of the ISS, would you get the same answer?
You would get the same answer because you'd get
So
twice
31,
the angle here,
yeah.
but you'd also have
what was
twice
the angle we
angle.
got again? We got 0.00768, didn't we?
Yeah.
Yeah.
Yeah. Okay, so I would expect 31.6 ISS images to fit across the moon. That's what I would expect to get.
Now,
And that looks
What
much more correct in terms of the photograph. If you look at the photograph that Anthony's got, it looks far more like it would be 30 or so going across than
what
just
I would
15
it's
or
what
16.
I would expect to get. That answer is what I would expect. I would to get about 31, 32 images of the ISS across the moon, not 16.5. I don't know whether you agree with me or not, but that's my calculation.
I do, and I'm just multiplying that angle.
Hmm?
And let's see what we get.
When you say images, you just mean images, not actual like ISSs, right?
No, of course not. No.
Okay.
If you stack that image, and if you were to cut that ISS image out of the moon photo that he's got and put them side by side, you'd get about 31, 32 of them across the diameter of the moon. That's what I would expect if the ISS is 110 meters wide.
Well, can I just say something here at the moment? The point that you've just made with half
done
the
that,
triangle.
Anthony, and found out how many?
So the angular size of the moon, as people have measured it, is
about half a degree. It's
31 arc minutes. It comes out at, I think, it says 31 arc minutes or half a degree. When I do the calculation using your figures or the figures that we've just calculated there, I come out with 0.41 of a degree, but I think, it's
and because you're
given the experimental error here,
you've used the largest distance to the moon. That's why.
Yeah.
Okay. So, but the average distance is only 385,000 kilometers, not 410, and it actually gets closer than 385,000 too.
Yeah.
So that half degree or 31 arc minutes is the average size, angular size of the moon, not the. So here, what we're calculating is at its smallest.
So the ISS image actually confirms the size of the moon and the distance to the moon as.
I haven't seen the actual photo.
Yeah,
I haven't seen the photo. So
Anthony, put the photo up.
I'm going to stop sharing now, and can Anthony put his photo?
Let's not jump the gun. Let's get the maths established. So
we're not jumping the gun, mate. We've just done the maths.
We have just done the maths. But we would expect to fit around about 31, 32 of them in there. So how many do fit?
Right, just wait. Let me answer. The problem we've got is that both of you two have got different results than what the other two guys did. So what I'm doing at the minute, I'm literally uploading the maths that was done. So Nathan was just showing it on screen. Then you could see that I'm uploading the actual maths. I'm going to leave it unlisted, Paul. I'm going to put you a link in the side chat. What I'd like you to do,
why are we even doing this? Wait, if like it doesn't even matter because we're just talking about images across the moon. It doesn't give us any real data or anything at all.
I would be interested to see the photo now and actually count how many of those fit across.
Yeah.
Well, I can
make
that.
4. I think the reason
the
is
problem
because
I have is that two physicists on the ball side have got different maths answers to you. So I'm not saying you're wrong. I'm not saying they're wrong. But what I'd like you to do, Paul,
I can't make a judgment on that because I haven't seen.
Answering a slightly different question, Anthony.
No, they're answering the same question. That's why I was very clear.
Because you're not very good at putting your questions. Is the point?
Yeah.
Right. Okay.
So I have a question.
I was very clear right the way through that we were trying to calculate how many international space stations would fit inside the moon. I don't know how I can be any clearer.
Yeah.
Right.
But that question can be interpreted in lots of different ways because it's a bad question.
Only to you.
No, it's a bad question, Anthony. You can say
clear,
on
Miles.
that picture,
how many
or you can say in real life, or you can say from some other perspective. So how many fit inside is not an accurate way of phrasing the question. So the person answering the question answers exactly the question that you want them to answer.
Maybe it's not an accurate way to you, but it was accurate enough to be able to do the maths.
A hard copy of those calculations for me.
The question.
Right. So this is what I'm doing, Paul. I'm uploading the file where the maths was done. Okay. And what I'd like you to do is look through
rules going for like who can talk and ask questions and like I don't know who can just rabble crap the most. I don't know because I can rabble too.
So
like this is what happens. We just
Marcus, stop a sec. Did you understand any of the explanation for what we were doing? Did you understand any of that math?
I did. I did understand what you just did there a little bit. Like I'm not the greatest, but like, okay. First of all, I would like to say, what's the point of even doing that if it's just images like across the thing? I don't care if there's 300 or 500 in there because it
What I
doesn't really
want to
tell
do
me.
now is I want to see the picture and I want to see how many actually fit there.
I think
I've done all
you're on
these
there, bro.
calculations and I haven't
I
even seen the picture.
wait. I
So,
appreciate what was
Paul,
just done. I appreciate very much what
Paul,
was just done, and I have another question, and that is like if you had just a calculator and pen and paper, is there a way for you to figure out distances of bodies in the sky?
well, no,
No,
you've got to take observations. You've got to take
absolutely.
observations on
Okay,
measurements in the sky.
okay, and like so, how like what's the simplest way of doing it? Sorry,
Of doing what? Taking the
of doing
distance to the moon.
that. Like, how many observations exactly would you need? Like, would you just need like say 3, and
Well,
then
you could get an idea from doing 2 observations. You
Yeah.
take one, it's often done with stars near to the moon and parallax. So you take an observation from one location on Earth, an observation from another location on Earth, and then you line up the moon exactly. The stars won't line up because of parallax, and you can use that observation to calculate distance.
Yep.
okay.
That's a relatively simple procedure. It's not complicated at all.
Because I'd be much
Paul?
more interested in learning something like that will give us actual data, like
It's been done.
Yeah, that is
Dozens
actually how Cassini, and I think it was 1672 or thereabouts, he actually measured the distance to Mars by using parallax, and it was before that they knew the relative distances of all the planets from the sun, but they didn't know the actual distances. They had the ratios, like they knew, for instance, that Jupiter was 5.2 times further from the sun than Earth was, but they didn't know the distance from the sun to Earth or the distance from the sun to Jupiter. They just knew that it was 5.2 times further, and they knew this because of Kepler and his laws. He derived his laws from very, very careful and accurate measurements that Tycho Brahe made. Okay. And then Cassini came along and he measured accurately the distance between the Earth and Mars. And so by knowing that distance between the Earth and Mars, they could then deduce the distance between the Sun and the Earth. Quite simply, it's not a complicated thing at all.
Okay,
Paul.
so what's the first easiest thing to measure?
Well, you need to take 2 observations to whatever the distance it is that you're measuring to from 2 widely spaced points.
Okay,
So you can get the parallax.
Okay.
Yeah.
Paul.
So what? Yeah.
Well, thanks for letting us.
I'm nearly finished uploading the original maths that was done, and at this point, I really want to show the picture too.
Yeah.
But I really want to.
Can we look at the photo while I'm waiting for that to come?
Hang on, listen. I really want to get a consensus on the maths first because there's a disparity between the maths. So until we get a consensus, I want to hold back with it because I want you to either agree with their maths that you made a mistake or that they've made a mistake and point it out. Because either way, there needs to be a consensus with the maths. Do we agree that's a fair position?
Oh, yeah, I guess so.
Because we've got ages on the show yet. So I've got it's saying about 3 minutes remaining for the link. So what I'll do is I'll send you a link in the side chat. And then I'm hoping that you'll drop yourself on silent while you go and check through what he does and then come back and say, yeah, this is what it is. Yeah.
So you're uploading it to a Google Drive or something that I can have access to see what the
someone would let me share my screen. I can probably show a photograph that simply illustrates that the calculation is not right. I just need to find the image that I just saved.
Well, we've already done it, Miles. So don't worry too much about that. We need to get consensus on the maths first because there's a disparity in the maths.
Well, this helps with the maths
Miles.
because what mathematicians very often do is make sure that the answer that they're getting is in the right ballpark. Because if it's not, then they know they've made an error somewhere and then go back and check it.
Yes, that's exactly what we're trying to do.
Well, this will show you whether you're in the right ballpark. I'm just going to should be able to get this up.
Well, here. Paul obviously understands the maths, Miles, and you obviously don't. So for the moment, we'll hang fire and we'll see if we can get a consensus.
Just
a
comment.
No, Anthony, just let me share my screen and post something up.
You can't.
Yeah,
we
can have a look. We can have a look at what Miles is showing us, can't we?
Yeah, you can go ahead, Miles, if you want to show something.
Yeah. Okay. I think I'm ready now.
Okay.
I think Anthony was just
I'm
covering because I was
sharing.
grabbing a drink and I was away from the keyboard, actually. So thank you.
If we can share this with everybody.
Deserves a shout, Nath. He was asking why was he not being welcomed.
Who's joined?
You can see here another transit photograph of the ISS where they've stacked images on top of each other to give a number. And if you count the number going across here, there's 15. Okay, but there's clearly now the orientation is wrong. So this would be the longest length would be from up and down here on the ISS. So you've got to imagine
these space in between.
You've got to imagine these flipped 90 degrees. But you could easily see that there's enough room for another ISS in between each one going across there, which would come out around about the 30 that we calculated. So 31 or 32 that we calculated. So it's obvious that I think that our calculation is correct.
Okay, but that would therefore mean that the other two physicists' mathematics must be wrong. So
well, they might have been answering a slightly different question, or they might have forgotten
consensus on the maths,
or used a radius instead of a diameter at some point and forgotten to correct for that.
Well, that's been corrected in the maths, Miles. So at the minute, we need to get consensus on the maths because there's a disparity. So don't be premature, Miles. We wouldn't want you to make a mistake.
So we are coming up on the 1 hour mark for this show, so I'm going to do a few quick links and then we'll go back to the debate. So if you are new to this channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, there is a super chat that runs alongside the show while it is live, and most importantly, if you would like to join the debate, there is a link in the info box below this video. With the page you are currently listening to me on muted, simply click that link to join the discussion and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected, but if you are, you will be warmly welcomed back on the next show. If you are currently watching this in the live audience, please share the show as it does increase the live audience, which in turn increases the chances of a more diverse panel. One last time, if you are new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate.
Okay.
Cool. So what's next?
I just noticed a comment in chat there from A4. He says, "Did you know that there was a guy called David Weiss that was killed in 9/11?" And I've just asked him for evidence of it, and I've looked it up myself. And on the 9/11memorial.org page, there's a huge list of names, and in there you can find 2 people called David Weiss, which is quite interesting. just as a curveball there. Right, I'm just waiting for this file to finish loading. It's nearly done. It's saying seconds remaining.
Just very common Christian and surname.
Weiss isn't that common, is it?
Yep.
It's fairly common.
Yep.
Okay.
While you're waiting for that to upload, Anthony,
3,500 people killed. Yeah.
While you're waiting for that to upload, Anthony, I'll just share my screen and just show you here what Cassini actually did. So this is a historical record of what Cassini. It was in 1672. He sent his colleague to France. French. I can't say that word. Guyana. That shit. Guyana. That's right. Yeah. And he stayed in Paris, and they both took simultaneous measurements of the parallax to Mars, and by that way they were able to calculate the distance to Mars. And then combining that with Kepler's theories of or measurements of the ratios of the distance of the planets, they were able to get for the first time a measurement of the Earth-Sun distance. That's how they did it.
I'd like to know which set of maths they used. Did they calculate for it being on a spherical surface, or did they calculate it being on a flat surface? Because obviously you get 2 different results if you put two different formulas.
All they had to do, it doesn't matter whether it's spherical or flat. All they had to know was the actual distance between the 2 of them, whether it be through the Earth or along a flat plane. It really doesn't matter.
It makes a huge difference to the distances.
It does make a huge difference.
Absolutely insurmountably different.
Yes, I know it makes a difference in the distance if you go over, but if they are assuming that the Earth is a globe, they would not have used the distance literally around the Earth between them. They would have calculated the distance along the baseline going through the Earth, knowing
the baseline
that.
being
No.
curved.
They'd have used a chord.
Yeah.
Right. So
Yeah,
well,
that's
no,
right.
they're
That's
not.
correct.
It's not. I don't think it does use a chord, does it? In the maths, I'd have to go and have a look at the maths again. It's a couple of years since I had a look.
Yeah. Well, you'd use the chord between the 2 points, not the actual curved distance around, because that would give you an error. And that's such a fundamental and basic and obvious thing that I doubt very much whether they would have overlooked that.
Yeah, but I reckon that's exactly what they've overlooked. That would be my assertion.
I don't think so. I don't think so.
It was smoking weed.
It doesn't matter either way. We've established that yes, if you use spherical or flat trigonometry, you're going to get very different results. We've established that.
They wouldn't, Nathan. They wouldn't actually be that different, especially if the distances involved were quite relatively small. So I think it's been done over a 1,500-mile distance. That one would have been several thousand miles because French Guiana is on the opposite side of the Atlantic in South America. Someone's done it, I think, between somewhere near London and Athens. It's about 1,500-mile distance now. That's going to be, if that was a flat Earth distance, it would be a little bit more than 1,500 miles, but it wouldn't be all that much more.
You calculate the distance to the sun
and
using...
the calculation actually wouldn't come out that dramatically different.
If you calculate the distance to the sun using spherical trigonometry,
magnitude different.
If you calculate the distance to the sun using spherical trig, you get 93 million miles. If you do the exact same calculation using flat trig, you get 3,000 miles. Those two are vastly different.
It is true, Miles.
Not true.
It is true, Miles.
That is true.
No, it's not true.
Are you just wrong, Miles? Sorry.
Yeah, you are wrong.
No, it's
Why do you think that's not
I
true,
missed
Miles?
that assertion. What was the assertion?
The assertion
It's a different trig. If you use a presupposition in the... Hold on, Miles. If you use a presupposition... Miles, I'm talking... Miles, if you use a presupposition in the trigonometry that you are on a sphere, the sun comes out at 93 million miles away. If you remove that presupposition that we're on a sphere, it comes out to 3,000 miles.
Not true.
Oh, God. You're just wrong.
No, he doesn't know. He hasn't done the maths to make that assertion. You can tell.
Listen,
Nathan,
case,
I've got the link. I want to give to Paul, but I'm not in the side chat. So could you pass the link to Paul through the side chat?
He admitted it.
The problem the flat Earth has is it comes out differently for each time you do the calculation at different distances.
Yes,
on the baseline.
Right on that one. That's correct, Miles.
Yep.
Okay. It only comes out to 3,000 miles distance for one pair of distances.
Yep.
Every other pair of distances you use on the flat Earth, it actually comes out to be a totally different distance. And therein lies the problem for flat Earth, that it's not consistent, that different people, different distances apart, will get different distances to the sun. And that is the problem for the flat Earth, because it's not consistent.
Well, we'll address that in a sec. Paul, the message is in the side chat for the actual maths that was being calculated. Could you vet through that and come back to us when you have a look at it?
It's a video, is it? Okay.
Yeah, it's of all the maths. So you'll hear him talking about it and applying the maths. So if you think he's made a mistake, then let us know. If you think you've made a mistake based on the maths, let us know.
It's going to take him more than a couple of minutes to study a video, though, isn't it? Let's be honest.
I know. It is. He may have to come back.
This is a 46-minute video, Anthony.
Wow, really? Bloody hell, Anthony.
Yeah. Well, I'm not going to wait 46 minutes. Can we come back to this next debate, maybe, and I can tell you an answer to the maths?
All right, that's a fair point.
I think that seems sensible. I think that seems sensible, Paul.
To see whether they're right or wrong.
Sure. We'll conclude it in the next hangout. Okay, that's fair.
Okay, because that's ridiculous, asking me to watch a 46-minute video to find out what they've done wrong in the mathematics.
No, but we do need a consensus in the maths. Okay? Do we agree?
Yeah. Okay.
You agree?
I have to go, I'm afraid, guys.
I will look at it, Anthony, but I'm not going to do that right now. We'd be better off discussing something else.
Thank you. Miles has got to drop, I think. Thank you very much, Miles. You've been excellent as ever. Thank you.
See you guys later.
Thank you. Bye-bye.
Check out Soundly's latest video, folks.
I have. I've already looked
from his test. Absolutely brilliant stuff.
It is.
Okay, see you later.
Yep.
And whilst Miles has gone, maybe now we can talk like without interruption, which is cool. Make 4, just to include you in the conversation a little bit. Is there anything that you want to talk about at this point?
Why? Because I'm the angry one.
No. Just because I don't want you feeling left out. I do have something I do want to address with Paul. If you don't, that's all.
Been joined by a new
cool,
guest.
just rubble,
Ronald,
rubble,
how you doing?
hugged.
Ronald, good to see you, my friend. Hello. How you doing?
Hello.
Good to have you here, Ronald.
Yeah,
Hey,
the
Ronald.
other one is blinking on and off. I can't really hear what you're saying.
Yeah, just mute the page that you joined from. So the page you were watching, just mute that.
Okay.
Just lost at Make 4. Hope he hasn't been sniped out. Let me know in the chat if you have Make 4. There's only a couple of people. I'll just start a new hangout. There's a good 50 minutes left. So sorry, guys. You carry on. I'm going to butt out. Sorry.
Okay.
I'm just opening up my file. Bear with me. Goes back to the Curie temperature discussion we had the other week. You cited a paper, and there were 2 papers that you cited, and we were talking about the supercritical temperature and the application of conductivity over magnetic ability to hold a magnetic field. Do you remember that conversation?
No, sort of vaguely, yeah.
Okay,
What's
you
the problem?
cited 2 papers, and we ended up getting a copy of one of them on screen, and we went through it. Do you remember?
Yeah, what was the
Nath,
problem with it?
Nath, would you share my screen so we can see my screen? I just want to go through something that was said that
No worries,
I'm going to
give me 20
call you on,
seconds.
Paul, and maybe
20
you can
seconds.
correct your position now. I'm guessing he's looking for it. All right, this is my video editor software that I use. And basically the conversation was about the Curie temperature and the Curie point of iron. And the point was when it becomes supercritical, it's neither conductive nor magnetic unless there's an external force to be applied.
No, that's false. That's false. You are not being honest, Anthony. You have no business saying that it's not conductive because all experiments show that it is conductive at those temperatures.
Which
you
is
have
exactly
no
what I'm
evidence
going to
to
play
say
now.
that it's not conductive.
Now, which is exactly what I'm going to play. I asked you to bring evidence to support the assertion that iron, when it's at supercritical temperatures, was either conductive or magnetic. That's what I asked for. So I'm going to play the bits where I'm asking for the evidence. Then I'm going to play the bits where you provide the evidence. And then I'm going to show you how the evidence that you provided was completely and utterly fallacious. Okay? So here's me asking for the evidence.
Anthony?
The same evidence I asked you for last time we ran into each other, Paul. The evidence that supports the notion that iron, when it's in its molten or solid state, critical temperatures, is either conductive or magnetic. Same evidence. That's what I'm asking for.
Okay.
So there's the first time I asked for evidence when it was supercritical, and I ask for it again now. So this is the second time I ask for it. It's just to be clear, so that people like Miles don't assert that I'm not clear with what I was asking for. This is the second time I asked for it.
Yeah, hang on. Used to obtain liquid state for above the normal boiling point. An estimate of critical point data for iron is given by using experimental data of the vapor pressure of liquid iron. So this is basically an experiment that they've done, and plenty of experiments like this have been carried out that determine and characterize iron at the kinds of temperatures and pressures that you'll find at the Earth's core.
Right.
Okay.
Hang on. What was the temperature that this was done at? Did you say up to 5,000 degrees Kelvin?
Yeah.
What's the critical
That's right.
temperature of iron?
Huh?
What's the critical temperature of iron?
Well, the critical point, it depends on the pressure. Okay? It depends on the pressure, right?
Right. So
the critical point, it depends on the pressure. It's much lower than that.
So yeah, okay. So can you show me how that molten iron?
What they're doing?
So at that point, Miles rather annoyingly interrupted, but I was asking whether or not this was supercritical or not. So you've presented something, or you've got a paper, and I asked specifically, was it supercritical or not? And then the next thing that comes back is this.
Riley.
Yeah.
Specifically, where does it say in either article that molten iron can be electromagnetic or conductive? Because you need both. Find either reference in either article and you can have your point. Neither article is talking about electromagnetic or conductivity.
Well, I'd have to purchase that first article to go through it and see there. But iron is conductive by its very nature.
Prove it.
A
No,
metal.
not when it's supercritical. It isn't.
Metal.
Not when it's supercritical.
It's a
it isn't.
metal.
So at this point, we're at the point where you're saying that iron, by its nature, is conductive, and I'm saying not when it's supercritical. And you've said that you've got a paper, and I said I'll buy it, but somebody graciously provided it in chat, and we spent ages going through it. And listen to what you say here. Is there anywhere in either article where it talks about the conductivity while it's supercritical, or its electromagnetic abilities? So that's 3 times I said it: supercritical, conductivity, magnetic. Okay, because I didn't see anything based on what you showed.
Yes, there is in that first article, but I haven't purchased the article. And in all our experience, Anthony, iron is.
So there is in that first article. You said that in the first article there was. Now, when we went through the article, we went through the paper in great detail. We read most of the relevant parts from it, and we got to the data table at the end. Now, the problem that we have now is that the data table at the end shows the values that they got this iron at when they got the results that they got. Now, I've brought the phase diagram back up on screen so that we can see the point.
Sorry, can you just close your chat page and make it a bit bigger? It's just tiny.
My chat page?
Yeah, on Skype, you've got the chat with our conversation up. Can you just get rid of that? Just make it a bit bigger, basically.
Yeah, hang on. Let me see. Do you mean... I'm not sure what you're referring to.
Maybe it's mine. Is it mine? No, it's definitely yours. Oh, don't worry about it. Just go through it. Otherwise, we'll chew up loads of time just trying to figure out how to get it a bit bigger. Don't worry about it.
It is yours. It's not mine. What we were able to establish was that the information that was presented in the paper gave values, which I'm going to try and get the values bigger so that they can be shown. How do I show this? Hang on, bear with me. I want to make this bigger. How can I make this bigger? You guys are not going to be able to see it, but I can read the values. The top temperature value, or the lowest temperature value that they cited, was 1,808. Then there's 1,608, 1,800 and something, 2,044, 2,347, 2,649, and the final one is at 2,952. So the highest temperature that they experimented on was 2,952. However, when we go back to the phase diagram for the iron, which is there, we can see that the highest value was 2,952. 2,900. Oh, it's in Kelvin. Hang on, that's in Celsius. So I need to do the conversion. Bear with me. So 2,952 Kelvin to Celsius should give us 2,678 in Celsius. And as you can see, 2,678 at 1 bar isn't supercritical. It hasn't got supercritical at this point. And that was the highest temperature that they recorded the thing on, which then takes me back to the point, well, this is a citation for supercritical iron, claiming that it was conductive or electromagnetic. So when you go back to the beginning of the paper, it said it was they were making estimates on what would happen at supercritical, because they didn't get it to supercritical, but you said that they did get it to supercritical. So basically, we had the conversation for about an hour about the contents of this paper, and it was completely, utterly, and 100% conjecture, because they didn't get it supercritical.
Okay, I'll respond to that. That paper that I showed the other day was an early paper. Okay, they've since done plenty of experiments since then, and some of the latest findings are that as you go higher in temperature and higher in pressure, the resistivity of iron actually saturates and starts to decrease as you go to higher temperatures and pressures. In any case, the point to be made here really is that in all of these experiments, the order of magnitude of the resistivity is millionths of an ohm. In all of these situations, the resistivity is in millionths of an ohm. In other words, there's hardly any resistance there at all, indicating that it is conductive. There is no evidence whatsoever to suggest that iron becomes an insulator at any temperature or any pressure.
So let's go back to the definition of...
If there was an experiment that indicated that the resistivity increased by orders of magnitude at higher temperatures or higher pressures, then yes, you could have your point. But the indications are that iron at higher temperatures and higher pressures actually becomes less resistive. In other words, more conductive.
But the point is...
So you're arguing against things that just aren't going to happen.
No.
Okay, I will share my screen now. Okay.
Hang on. Do we agree that once the Curie point's met and exceeded, which it was in all the experiments that we're talking about here, iron will lose both its magnetic properties, and unless it's replaced with an external field, it cannot be magnetic. It cannot be conductive.
It becomes paramagnetic. It does not lose its magnetic properties. It becomes paramagnetic. Saying that it loses its magnetic properties is false.
Okay, but it says it in black and white, Paul.
Being ferromagnetic to paramagnetic. And that means that it can still be magnetized. It can still generate a magnetic field.
Could you show my screen, Nathan, please?
Known and well understood.
Paul, what does it say? And what's the highlight? The bit that's highlighted in blue. The Curie point is the temperature at which materials lose.
I know what the Curie point is, Anthony. The Curie point is that temperature when iron changes from ferromagnetic to paramagnetic.
But that's not what it says.
It does not mean that it loses its magnetic properties. It means that it cannot retain a magnetic field when you take the external field away. That does not mean that it cannot generate a magnetic field.
So are you saying that the information on screen is wrong?
And we showed that we use non-magnetic copper in power stations to generate magnetic fields.
Paul, are you saying that the information on screen is wrong?
That is not true. The Curie temperature is that temperature for which iron becomes paramagnetic instead of ferromagnetic. That is what the definition of the Curie temperature is.
Well, I've got it on screen, Paul. Can you see what's on screen?
Let me have a look what you've got on screen, because I'm sure it's probably wrong.
Well, this is your science. Okay. So
yeah, it says in physics, material science, the Curie temperature the Curie point is the temperature at which certain materials lose their permanent magnetic properties to be replaced by induced magnetism. The Curie temperature. Now, have a look at what you've got on the side there. You need an applied magnetic field, but in a self-exciting dynamo, it's the self-exciting dynamo that provides the magnetic field in the first place.
And that's what I was asking you for evidence of.
The Curie temperature is defined as the temperature that a material becomes paramagnetic rather than ferromagnetic. That's what the definition of the Curie temperature is.
No, it isn't. You've got it wrong. What it is? What does
it is? So
read what it says on screen, Paul.
Absolutely, it is.
Read what it says on screen again. You've missed it, obviously.
I know, and you've missed the point. The key word there, it loses its permanent magnetic properties. That's what the definition of ferromagnetism is, Anthony.
And what does it say happens next?
Is when a material can be permanently magnetized.
What does it say happens next?
Paramagnetism is when a material cannot be permanently magnetized.
What's the next sentence, Paul?
That does not mean that iron cannot generate a magnetic field.
Right, that's what I'm calling you on. So read what it says in blue now, Paul.
What?
Read what it says on the screen right now. So it loses its permanent magnetic properties. We're agreeing at that point, but what does it say about the next line?
By induced magnetism, and I have been over this point too.
Right. So
I have told you that a self-exciting dynamo induces its own magnetic field. You do not have to provide an external magnetic field.
Yeah, you do.
It provides its own magnetic field.
So this is what I'm asking you.
I've been through this with you, Anthony.
And you haven't produced any evidence, Paul.
The free electrons in the moving iron constitute an electric current. An electric current produces a magnetic field, and the magnetic field magnetizes the iron. That
Paul,
is
can
what
you prove
happens.
that that's the case?
That is what happens.
Prove it.
Okay?
Prove it.
For goodness sakes, Anthony, we understand
No, you understand.
hydromagnetodynamics. All right?
Yeah, but I'm saying that iron cannot create its own force, its own field. You're saying it can. I'm asking you to prove it. Right, prove it then.
It's a conducting metal. All conducting metals, all conducting fluids can be used in hydrodynamics.
But do we agree that once the Curie
conducting fluid, and iron is a conducting fluid.
Paul, do we agree that once the Curie temperature is met, that it loses its ability to be magnetic unless it's replaced with...
We've been over this. How obtuse are you, Anthony?
Seriously,
you're not.
Sorry, guys. Just make a quick introduction. We've been joined by Tim Osman. Just make a quick introduction to Tim. How you doing, Tim Osman?
I'm good, but dude, Riley, you don't know what you're talking about, man. And this guy has tried to explain it several times to you.
Yeah,
but what you try to do is catch people in little tit for tat arguments where really
using their evidence against
you don't know what you're talking about. You're making assertions as if you know that iron will lose its magnetic properties. How would you know that? From a Wikipedia article, dude?
We've also
Give me
been
a break.
joined by
You're a
Grim
joke,
V.
man.
Grim V, how
What
you
a
doing?
joke!
Here. How you doing, Grim?
Hey Nathan, hey Paul.
Good to see you.
Hey,
Anthony. Oh, you're gone.
What's happened? Hello?
Hello?
Can you hear me, Grim?
I hear you, Paul.
Yeah, okay. Where's everyone else gone?
I don't know, but
I'm
that's
still
just
here,
the
I
way
was
the cookie crumbles, huh? Oh, there's Nathan, it seems.
So Nathan's still here, Paul's still here, Grim's still here. So so obviously Tim's left, right? That's fine. Paul.
Okay.
We understand that at the Curie point, iron loses its magnetic charge. We agree. Okay? Is that okay?
It loses its ability to permanently hold a magnetic field. How many times do I have to tell you this?
I agree with you. And we agree that the temperature's been met. So at the point when it's at supercritical, unless it's got an external charge providing it, or it's a self-perpetual machine, it ain't going to be able to be magnetic. So I'm asking you for evidence that proves that iron is able to do what you say it is. And to this point, Paul, you haven't produced any. Even though you're arguing it, you haven't produced any.
Any conducting metal will be able to generate a magnetic field if you move it. It does not require it to be a ferromagnetic material. I have shown you this. We use copper, which has no Curie temperature. It is paramagnetic right from the start. And yet we use copper in power stations to generate magnetic fields in self-exciting dynamos. That in itself is proof that we can do this with non-magnetic materials.
Prove it, Paul.
I can use an aluminium ring.
It's already proven, though.
It's already been proven.
Paul,
you just haven't. You just don't want to go and find the evidence for yourself. You want somebody else to do your research for you, Anthony.
Yeah. Paul, there is no evidence for it. That's the point.
There is.
Prove it then, Paul.
What do you want me to prove? You want me to prove that iron is conductive? We've already shown you that iron is conductive at any temperature and pressure.
Paul, you haven't shown any evidence to show that iron is conductive at supercritical temperatures. You haven't done it.
I think I have.
You might think you have, but I'm telling you haven't.
Okay. How about we just share my screen? Okay.
And whatever
it loses some conductivity, but it's still conductive.
It is. It's conductive. All right.
Prove it.
Okay. Here we go. On my screen, we have some measurements. They are not taken up to the high temperatures and pressures that you see. I want to know. But what this does show is that the resistivity curves over and it starts decreasing as the temperature and pressure increase, meaning that it's becoming more conductive.
Well, is that answering the question, though? The question is, can you show that iron is conductive? Not that it might be more resistive.
Are you concerned? Are you wondering like what happens when it's heated up to, let's say, a plasma?
No, I'm asking for evidence that proves that iron, when it's supercritical, is. I'm asking for the evidence that proves that iron. I'm asking for the evidence that proves that iron can create its own magnetism or is conductive at supercritical temperatures.
It is conductive. We've already been through this, Anthony. The resistivity of iron at those temperatures and pressures is in millionths of an ohm.
Okay, so let's give you that for the sake of discussion. Where does it come from?
Conductive.
Where from?
All metals are conductive.
Where from?
Liquid, solid, it doesn't matter. All metals are conductive. That's what metals do. They have free electrons that conduct electricity.
Not above the Curie temperature, Paul.
They do. The Curie temperature has nothing to do with the conductivity, Anthony.
Yeah, but Paul, it means that there's an external source required.
Absolutely nothing to do with the conductivity of any material.
Let's be
clear. The Curie
clear.
temperature is simply that temperature where the material becomes paramagnetic instead of ferromagnetic.
Let's be clear. Your position is that iron can generate its own field. My position is there's no evidence to prove that that's true. So, again, your cited paper doesn't do what you say it's supposed to be doing. Where's the evidence that iron is able to do it?
Right, I'm going to talk over all of you and do a few links as we have approximately half an hour left on this stream. So, if you are new to this channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, if you've been enjoying these debates, toss me a buck or two in the super chat. And if you would like to join the discussion to contest anything that is being said currently, simply mute the page you are currently watching and click the link in the info box below this video. There are a couple of rules. Please do not swear. If you do, I will eject you. And if you are ejected, please don't try to rejoin using sock accounts. You'll be warmly welcome back on the next stream. Please share the show on Facebook, Skype, Twitter, and all of the social media that you have at your disposal, as it increases the live audience, which in turn increases the diversity of the panel. One last time, if you're new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon. As I say, we have about 30 minutes left on this stream.
Okay. All the evidence suggests that iron is conductive at any temperature and pressure, Anthony. You have yet to provide any indication or any evidence of any suggestion that iron is not conductive at those temperatures and pressures. You're running around asking people to prove something that has good evidence to support their assertions, and yet you provide no evidence whatsoever to support your claim that iron won't be conductive at those temperatures and pressures. So how about you run around and try and find some experimental data that indicates or suggests that iron isn't conductive at those temperatures and pressures, because that's the claim you're making.
Paul, again, once the Curie temperature is met, iron loses its magnetism.
And I have already told you the Curie temperature has nothing to do with conductivity. And
So
I have
it
already
requires an
told you
external field,
that it is irrelevant to a material being able to generate a magnetic field.
But you haven't produced evidence that shows that iron does that. And that's the claim. That's the assertion that we have an iron core. You believe it to be true, and there is no evidence. So even though you believe and claim that there is, you haven't produced any. So you can put it onto me if you wish, but it's your assertion. He who asserts must prove. Your assertion is we have an iron core. My assertion is prove it.
No, your assertion is that it's not.
Generation of these fields in the lab, two teams in year 2000 forced liquid sodium into complex but non-turbulent flows using physical barriers that deflected the fluid along precisely defined paths. Now, the French VKS collaboration, which includes the École Normale Supérieure ENS institutes in Paris and Lyon in the Atomic Energy Commission, CEA, in Siclay, has, I don't know if I said that right, has created a self-generating magnetic field with the less contrived flow. They place discs equipped with curved vanes at each end of half a meter long cylindrical tank filled with liquid sodium. Rotation of these propellers, in quote, in opposite directions up to a 26 revolutions per second created a turbulent flow that generated a magnetic field. The field only appeared when the propellers were made of iron, which modifies the field near its surface. Compared to the previous experiments, the flow is less constrained geometrically, says team member Stéphane Fauve of the ENS in Paris, although he admits it's not as free as in Earth's core or in other planets, stars, or galaxies with magnetic fields. The spontaneous field appeared when the average flow speed throughout the liquid was surprisingly low.
Grimv.
So there is demonstrations of these fields being generated through mechanisms similar to what we are trying to convey as the mechanism of the electric and magnetic field from the turning of the iron molten core.
Grimv.
There you have it, buddy. Are you satisfied?
No, 3 questions, Grim.
And
one.
The point that Anthony, that liquid side, yeah.
Grim,
I'm out.
Let me ask you 3 questions. You said that it was sodium. Was this done with iron or was it done with sodium? Grimv.
They only appeared when they used the iron propellers, the fields.
Yeah, but what was the substance in use?
So
was it sodium
was a
or was it
necessitative.
Grim, what was the substance? Was it iron or was it
value?
Was it sodium or iron, Grim? Come on.
Both.
No, it was sodium, wasn't it?
Well, yes, and iron.
Second
the propellers
question,
were iron that spin.
Grim.
So the iron had to be present.
Grim, second question. Was it supercritical or was it just beyond its melting point?
I don't think they were so concerned with your issue there.
Was it supercritical or not?
Because it was molten.
Right, but was it supercritical or not?
So it doesn't matter, right? Supercritical.
That's
I mean,
specifically what we're talking about there,
Grim.
That's specifically what we're talking about, Grim. Sorry to
Is that
be
a
rude and
particular
interrupt.
example of how you're confused about magnetism and electricity?
Sorry
was
to
it
do this,
supercritical
Grim.
or not, Grim?
Please give
over
him
and
an
over
answer,
again
because
because you
otherwise
think
we'll
it has
go over
something
this
to do with the
10 years.
conductivity of the material instead of actually
please
the
give him an
magnetism
answer.
flipping itself to
Grim?
paramagnetism.
Was it supercritical or not?
You're not really familiar with that stuff, though, are you?
Oh, Grim,
Honestly.
please give him an answer.
Just
Let's
answer the
just be
question,
honest.
Grim. Was it supercritical or not?
Well, obviously, they didn't tell us. They didn't say, "Oh, well, let's see if it has magnetism."
They did. They told us. You read it in the first 3 lines.
No, I didn't.
Read the first paragraph.
No, you're talking about paramagnetism. That's generated by the electric field, knucklehead. That's what we're saying.
Right, but it wasn't supercritical. It wasn't
Yeah,
iron. And it was
it's not talking about did it have magnetism to the liquid sodium.
right. So the point that you've produced is that sodium can do it when it's at atmospheric temperature.
Permanent.
Grim.
You're
The
not
point you've shown is that sodium can produce its
explaining
own force
everything.
at
Like
pressure
you hold
that's
together these
Earth-based.
complex thoughts like in separate where they go.
Grim,
You conflate
Grim.
them.
All
You
you've
smash
shown
them
is that sodium can do it at room pressure and not at supercritical temperatures. However, the claim is that iron can do it when it's supercritical, and I'm saying there's no evidence to support that. Paul's not produced any evidence.
You're
to
standing
support it.
around on a big
You
giant
produced
argument
evidence
of
that's
nothing.
not the same either. So at the moment, we've had 2 people that's produced evidence that does not support the assertion that iron can generate its own field. So again, I restate my position: is there any evidence that shows that iron can self-perpetuate its own charge? So far, there is none.
You're missing it right here. It does support the idea. The outer core of the iron would spin slower, right? But it would be not as molten, wouldn't it? there would be solid iron moving at the ends of the core, wouldn't there? Because that's how the skim works. Have you ever heated up something like that, molted up some metal, and you saw the impurities and the outside edge would cool off as well?
Yeah.
Well, that's
So
a lot of iron.
let's read
buddy.
what you highlighted.
It would
By
be less
including the
dense, it's
saturation
floating
effect in the
there.
extrapolation of the measured electrical resistivity to high temperatures, they found resistivity of values of about 0.4, 0.5, 0.5, and 0.4 times 10 to the power 6.
Supercritical
Ohms
instead
at
of just
100.
some part of the core, and then the rest is you don't talk
Right,
about it.
so
There are
Grim,
other stuff that's around there.
This is not Grim.
So you're
this
not-
is not showing
that's-
evidence that iron can generate its own field, its own power. So
You're
the
just
point
talking
is,
over
the evidence that
dude.
we're asking for is that iron can produce its own power. All that's
Anybody
talking
re-
about is its
No,
resistivity.
you have that is absolutely dishonest of you, Anthony. You have provided no evidence whatsoever that it can't. How dare you claim that this is evidence that it can't?
He's not asserting that it
have
can,
no
though.
evidence
not
You
what I
are.
said.
Paul,
That
you're getting
is a
very angry.
dishonest
You're the one
claim.
making the assertion that it can, and he's asking you for evidence to support that, and now you're
I
getting
know,
very angry,
but-
saying, you
I
can't
know,
prove it can't.
But him
That's totally
saying that it's
unreasonable.
evidence that it can't is
Well, that's
dishonest.
totally unreasonable. He's not pretending there's an iron
No,
core that's
not.
got a supercritical core that can generate its own magnetic field. You are.
Yes.
That's right.
Paul's
but him
misunderstood.
claiming that there's
Right,
no
so prove
evidence
it, Paul.
suggests
Don't
it
demand
can.
that he
It's-
proves it doesn't exist. You prove that it does.
Because the
Okay.
assertion,
Yeah.
your assertion, Paul, is
What
that
I've
iron.
highlighted here is it shows that the resistivity is so small at these temperatures and these pressures.
Right.
That
But your assertion is that
iron
it creates
is-
its own
iron
field.
is conductive.
Your
Right? Do
assertion
you
is
give
that it
me
creates
iron
its
is
own power.
conductive at those temperatures and pressures?
Your assertion is that it creates its own power, Paul. It self-perpetuates, essentially.
That's
I'm asking you
correct.
to prove that iron
Are
can
you
do it.
Are you giving me, Anthony, that these figures here show that iron is conductive at those temperatures and pressures?
You're missing the point again. I'm asking you to prove
No,
that it
Anthony,
creates its own
Here
charge.
we have resistivity values of 0.5 of a millionth of an ohm.
But that's not showing that it's producing its own charge, Paul.
What
That's
it's
the claim
showing is that it is conductive.
Right, but you're
So
saying
stop
that it creates
saying-
its own
stop
charge.
asserting that iron is not conductive at those temperatures and pressures, because it is.
But it
and they've
requires an
measured it.
external field.
Okay.
But it requires an external
Right.
field, Paul. And I'm asking you to produce the
No.
evidence that iron can self-perpetuate.
Right. Any conductive material, when it is
Iron.
stirred, can create
Iron,
a
Paul.
magnetic field.
Iron, Paul. Not any. We're specifically talking about
fluid.
iron.
Any conductive fluid can do that. Okay.
Prove that iron can do it.
Does not have to be iron.
Yes,
right?
it does, because
Any
that's the claim.
Any conductive fluid can do it.
Prove that iron can do it.
Any conductive fluid does it. That's the way magnetohydrodynamics works.
So you're going to accept that you can't prove iron, but on the basis that any.
Does he think only iron is in the core of the Earth, though? There's no
Well,
nickel.
that's what the
or-
claim is. That's what the
just
claim is.
iron. Yeah, I think maybe you're confused.
We're saying we don't know.
All
You're
the
saying you
details
do.
first.
That's the thing here, Grim. We're saying we don't know what's in the core. You're saying we know what's in the core. It's iron.
No, what I am saying though is that iron can do what it's proposed that it can do.
Sure, just prove it.
Being that it's got some of the same symmetry as the other liquid metals and their dynamics and their abilities to do the same thing.
So
at
prove
different
it.
rates.
Simple request.
Hang on.
That's what Hannes Alfvén won the Nobel Prize in 1970 for, I think. Magnetohydrodynamics.
Okay. Try again.
Just be careful, Paul, that it actually answers the question that iron can self-perpetuate when supercritical.
Right. Magnetohydrodynamics, also magnetofluid dynamics or hydromagnetics, is the study of the magnetic properties of electrically conducting fluids. That includes molten iron.
Examples
of such magnetofluids include plasmas, liquid metals, salt water, and electrolytes. Notice they don't say some liquid metals. They include liquid metals.
Right, and
The
notice that
word
they don't talk about iron and they don't talk
magnetohydrodynamics
about
is derived
supercritical.
from magneto, meaning magnetic field, hydro, meaning water, and dynamics, meaning movement. The field of MHD was initiated by Hannes Alfvén, for which he received the Nobel Prize in Physics in 1970. Now, this next paragraph is the important bit. The fundamental concept behind MHD is that magnetic fields can induce currents in a moving conductive fluid, which in turn polarize the fluid and reciprocally changes the magnetic field itself. The set of equations that describes MHD are a combination of the blah, 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 blah. So they've actually got equations that allow us to calculate how this works.
So, Paul, let me respond. Just scroll up a little bit on the page because the top part's chopped off on my screen. Just scroll up a little bit. Right, so let's apply this. The fundamental concept behind MHD is that magnetic fields can induce currents. I agree. In moving conductive fluid, I agree, which in turn polarizes the fluid and reciprocally charges the magnetic field itself. I agree. The evidence request is that iron can do this all by itself. The requirement clearly states that magnetic fields can induce currents, but not that they are self-inducing. So whilst your point is accepted, my request still remains, can iron self-perpetuate or not?
Yes, it can.
Evidence, please.
This happens with, and the key part here is, can induce currents in a moving conductive fluid. Is molten iron a moving conductive fluid?
But the key word there, Paul, is induce, not self-perpetuate.
The key word here is moving conductive fluid.
No, Paul, induce. I agree with the word induce. I'm asking you to show self-perpetual.
That's right. It can be induced in any moving conductive fluid.
I agree, Paul. They can be induced. Your argument is that it self-perpetuates, not that it's induced.
That's correct. That is correct.
So can you produce evidence that iron self-perpetuates?
If it produces a magnetic field, then magnetohydrodynamics will allow it to be a self-running dynamo.
So produce evidence to that effect on iron.
This is the whole point here, that magnetohydrodynamics, the fundamental concept, moving conductive fluid, right?
With an induced
in turn
current,
polarizes the fluid and reciprocally changes the magnetic field itself.
With an induced current, Paul, not self-perpetuated, induced.
We've been joined. Sorry to interrupt you, Paul. We've been joined by. Sorry, Paul. Sorry, bear with me just 1 minute. Sorry, Paul.
Do you understand?
Bear with me just 1 second, Paul. I just need to introduce Curved Water. How you doing, Curved?
Sure.
Good.
Hi, Curved.
Does Anthony understand what induced means? I'll be quiet now.
Do you understand what induced means?
It distinguishes itself from self-perpetuating. So, Paul,
what does induced mean, Anthony?
Provided by an it just means allows it to come from the outside.
Okay. Do you understand what an electric current is, Anthony? What constitutes an electric current?
No, I don't.
Paul, do you understand what induced means in this context in relation to...
Would you agree that a moving charge constitutes an electric current? If we move charge from one place to another, that constitutes an electric current.
Yes.
Agree?
Sorry, Paul. Could you answer the same question that Curved asked?
What's that?
Could you answer the same question?
I'm not sure what you're getting at.
What do you take to be the meaning of induced?
Yes, induced means that something can induce something external can induce magnetism or induce electricity in something else. That does not necessarily mean that the field has to come externally.
So your position is that it self-perpetuates?
Yeah, that's right. All right.
Right.
So like a transformer.
I'm asking you for the evidence that iron
in a transformer, we have a magnetic field inducing a current, which in turn induces a magnetic field, which in turn induces a current. That's a self-perpetuating type thing. Yes.
Right, Paul, I'm asking you to produce the evidence that iron does self-perpetuate. I accept that iron can be induced, but I'm not accepting that it self-perpetuates. So I'm asking you to produce iron.
Well, that's
doing
shifting
that.
the goalposts, Anthony.
No, it's not. It's the same thing I've asked for all the way.
Anthony.
I have not changed my position.
It is.
Right.
Right, because I am trying to explain to you how the iron generates a magnetic field in the first place. Why
No, you're
you
not. You're
don't
trying to point
need
out that it can
an
be induced.
external magnetic field to generate
No,
the
Paul.
magnetic field in
Paul,
the first place.
No, you're not. You're trying. All you're
I am
showing
trying-
is that iron can induce a current, not that it perpetuates one.
Right? Okay. Follow me. Did we agree that a moving charge constitutes a current, an electric current?
Yes. Can I add
Okay.
to what you're saying, brother, when you're done?
All right. A moving charge constitutes an electric current. All conductive fluids have freely moving charges in them. When those conductive fluids move or convect or change position, that constitutes an electric current, because literally what you are doing is moving those charges around, and that constitutes an electric current. It is well known and well understood that an electric current produces a magnetic field.
Right,
so
that's the
any
point.
time you move electric charges, you produce a magnetic field, and that includes molten iron. It includes all conductive fluids. By their very nature, they have freely moving electric charges, which, when those charges are moved, constitute an electric current. And when an electric current is produced, it produces a magnetic field. That is a fundamental concept of physics that you cannot argue with. It can be easily demonstrated in any laboratory.
Okay, and I don't disagree with that, Paul. What I'm asking,
you don't have. I'm trying to explain how it self-perpetuates. Okay?
Right, but I'm asking you
once
to prove
start
that it does.
So once you start that iron moving and it generates a magnetic field, that magnetic field then affects the way the particles move.
And I'm asking
And
you
that
to prove it.
Changes the magnetic field, which changes the way the particle moves. And that is how it self-perpetuates.
I understand the logic. I'm asking you to prove that it does it.
Excuse me, Anthony. I'm going to add something to this. I already asked earlier, so you're stepping on my toes right now by stepping in. So I also wanted to add, when he was finished, something to this dynamo that has not been thoroughly investigated until recently, and it is the actual dynamo of the same exact magnetohydrodynamic effect happening on the outside of the planet on its way in, as well as the solar atmosphere is a plasma, and the magnetosphere is a magnetic field moving through a plasma, also
Grim,
generating.
I agree with that point. That would satisfy the definition of induction. But I'm asking Paul to prove that it self-perpetuates.
This is. Oh, I'm just going to get interrupted. Never mind. This has been rude.
Well, I'm asking for the evidence that iron self-perpetuates, not the logic and reason behind it. I'm asking that it does. Now, I know Paul doesn't.
I entertained your stuff, right? But then I also made it a vacuous argument by interjecting that the mechanism can also happen from the atmosphere outside.
I agree. You're arguing that it's induced.
Vacuous anyway.
Grimf, you're arguing that it's induced, and I agree it is induced from the atmosphere outside. Paul's argument is that it self-perpetuates. I'm asking that for the proof that that does happen, and it doesn't because
one is supporting capacitance and driving itself long enough to get the overture of what's happening from being pulled in from the plasma in the atmosphere.
But where's the evidence that it can do self-perpetuation?
Well, I guess the evidence, Anthony, is that we have a magnetic field around the Earth and we can measure it.
Love it.
Yeah, but
you would get there in the end.
That external field around the Earth, Paul, is the external charge that provides it. So again, we're back to the point, where's the evidence that it self-perpetuates?
The pattern of the magnetic field, indicates that it originates from internally, not externally.
Prove it.
The majority of it. The pattern of the magnetic field itself. You can see that the way the pattern of the magnetic field of the Earth works it's clear that it generated inside the Earth and not external.
Prove it.
Because the magnetic field lines cut through the Earth's surface.
So can I ask?
Going on.
Sorry, Paul. Can I ask a quick question? How do we see that?
I can show it.
We got a diagram or something. Maybe we could just show that to the audience with.
Well, it seems like the data, not to argue with you, Paul, personally, but it seems like the data has been supporting the current sheets from, the ring around the polar regions as with a little Birkeland current, connections connecting and reconnecting all over the place out there, kind of showing that there's an external drive to the spheroid, not a not so much internal as once was thought, by gravitational core burning out pressure kind of ideas. But
I
that's
agree with
still
that, Grim.
neither here nor there as far as the shape of the Earth. It actually demonstrates more of the spherical nature than ever, because then you understand that, through those plasmoids and magnetic fields, you see the toroidal spherical shape of all matter. And
I agree with that comment from Grim. It shows that it's an external field that's going in. It's not self-perpetuating.
All right, the image that I've got up here, it's not a very big image, I'm sorry about that, but this illustrates the shape of the Earth's magnetic field. This is not the true shape of the Earth's magnetic field. It is a very highly simplified diagram of the Earth's magnetic field, but nevertheless it will do to illustrate the principle here. I think we all know a thing called magnetic declination, okay?
Yeah.
Magnetic declination, or magnetic dip, sorry, not declination, magnetic dip, in that that if we measure the magnetic field using a compass on the equator, that the compass points nice and flat. But as we go further and further towards either pole, the compass starts to dip on one end of the compass. It's being pulled down. And that's because these magnetic field lines, if I can get my pointer on the right screen, it's because these magnetic field lines, sorry, my mouse pointer just doesn't seem to be coming up on the actual hangout. But in the top there, the magnetic field lines, you can see that they go in at more or less a 90-degree angle to the Earth at the top there and at the bottom, okay?
I agree, Paul.
And this indicates that the magnetic field cuts the Earth's surface at those points, so it's generated internally, right? It's analogous to a bar magnet that's on the inside of the Earth. Okay, so that's how, and this nicely explains the aurora, the southern and the northern auroras too, because as charged particles come in, they spiral around these magnetic lines and come in and get close to the Earth at the poles, at either pole. And that's where they interact with the Earth's atmosphere and generate the aurora.
Got about 60
so the
seconds
shape
left.
of the magnetic field itself indicates that the magnetic field is generated internally.
We've got about 60 seconds left. Just so you know, I've put an image of an azimuthal equidistant map with the magnetic declination on top of that, just so you can see it's on my screen now. But we have about maybe 30 seconds left, just so you know.
Nathan, would you just share my Skype
magnetic
screen
declination is a different thing. Anyway, go.
Nathan, would you just share my Skype screen for Paul?
Yeah, I'm sharing. You've got about 20 seconds.
We'll finish the show, Paul, with my assertion that if there is something providing an electromagnetic charge, it's external. No, not that page, Nathan. The Skype page with the webcam on it.
What?
I should be sharing my webcam page with you on Skype. Oh, hang on. Let me just turn off. Hang on. You should now see. Is my webcam on?
It will be in a second, I think. No, it's not coming on. You're running out of time because I'm just going to cut across you in about 10 seconds. Say what you need to say.
If the Earth has got a self-perpetual, if the Earth's got a core that's being powered by something, it's coming from the outside. It's not coming from the inside because it can't self-perpetuate, and there's no evidence to support that it can. That's my position.
And with that, I'm going to say, first and foremost, a huge, massive, enormous thank you to all of the live audience for joining this debate and, of course, for sharing the show. And a massive thank you to all of the debating panel for making this debate possible. Be sure to like, comment, share and subscribe. I've been Nathan Oakley, and I will see you all in the next video. Munchkin. I've got to end the show.